Hi everyone. In the last class, we discussed about the Laplace transform and some methods we discussed for finding the Laplace transform of the given function. Now we go for the inverse Laplace transform, which are very useful for solving the ordinary differential equation and integral equations also. Right here now the definition of the Laplace transform, we know that since the Laplace transform of f of t is equals to, here it is, we write it f bar of s or some capital F of s. Yes, this f bar of s is the Laplace transform of f of t. The input is function of t, the output is function of s. This function of s is called Laplace transform of the function of t, f of t. In the reverse process, yes, this f bar of s is a Laplace transform of f of t. Then what about f of t? If you take this t l to the right side, so it becomes L inverse of f bar of s is equals to f of t. This f of t is called inverse Laplace transform of the function f of s, and this L inverse is called inverse Laplacian operator or inverse Laplace transformation operator, right? So from the definition, what if we write Laplace transform of f of t is equals to f bar of s, that implies f bar of s, simply you can write it some capital F of s, that implies, or if and only if L inverse of f of s is equals to, here it is f of t, here the function of t is the inverse Laplace transform of function of s, function of s is the Laplace transform of function of t, right? This is the definition of the inverse Laplace transform. Next, some elementary inverse Laplace transform of some elementary functions. So by using Laplace transform, we are writing everything. Inverse Laplace transform of some elementary functions. First one, you know that Laplace transform of 1 is equals to 1 by s. That implies L inverse of 1 by s is equals to 1. This is considered to be formula. Second one is Laplace transform of t to the power of n is equals to, n being a real number and n is greater than minus 1. So which is equals to gamma of n plus 1 divided by s to the power of n plus 1, n being any real number, n being any real number with n is greater than minus 1. n is greater than minus 1 and s is greater than 0. s is greater than 0. That implies from this we can write it, you take out this L inverse of gamma of n plus 1 divided by s to the power of n plus 1 is equals to t to the power of n. As gamma of n plus 1 is a constant, you write this implies L inverse of, or gamma of n plus 1, L inverse of 1 by s to the power of n plus 1 is equals to t to the power of n. From this we can write the formula L inverse of 1 by s to the power of n plus 1 is equals to t to the power of n divided by s to the power of n plus 1. Here n being real number, being any real number, and n greater than minus 1 and s is greater than 0. This is one more formula, right? In the same way, writing one by one. Suppose n is positive integer. If n is positive integer, you know that Laplace transform of t to the power of n is equals to n factorial divided by s to the power of n plus 1. here s is greater than 0 and n is positive integer. So from this, L inverse of n factorial divided by s to the power of n plus 1 is equals to here t to the power of n, that implies n factorial is a constant. L inverse of 1 by s to the power of n plus 1 is equals to t to the power of n divided by n factorial. S is greater than 0, n is positive integer. Next, you know that Laplace transform of e to the power of at is equals to 1 by s minus a. S is greater than a. That implies L inverse of 1 by s minus a is equals to e to the power of at. It is for a. S is greater than a. In the same way, you can write it e to the power of minus at is equals to 1 by s plus a. That implies L inverse of 1 by s plus a is equals to e to the power of minus at. S is greater than minus a. Next, you know that Laplace transform of sin at is equals to a divided by s square plus a square. That implies L inverse of a divided by s square plus a square is equals to sin at, or a is a constant, better to write L inverse of 1 divided by s square plus a square is equals to sin at by a. In the same way, Laplace transform of cos at is equals to s divided by s square plus a square. That implies L inverse of s divided by s square plus a square is equals to cos at. Next, seventh one, sin hat cos hat. Laplace transform of sin hat is equals to a divided by s square minus a square. That implies L inverse of a divided by s square minus a square is equals to sin hat. That implies a divided by L inverse of 1 divided by s square minus a square is equals to here sin hat by or 1 by a into sin hat. In the same way, L inverse of Laplace transform of cos hat. Cos hat is equals to s divided by s square minus a square. That implies L inverse of s divided by s square minus a square is equals to cos hat. These are the inverse Laplace transform of the elementary functions. They are elementary functions. You know that the Laplace transform of 1 is equal to 1 by s. L inverse of 1 by s is equal to 1. Laplace transform of 1 by s to the power of n plus 1 is equals to, just recall 1 by 1 is st, that is t to the power of n divided by gamma of n plus 1, like that we written. Okay, next, these are the elementary problems. Next we go for some problems on this. Next we go for the linear property also. As Laplace L inverse of c1 of f1 of s plus c2 of f2 of s, f2 bar of s is equals to c1 into L inverse of same, the linear property in the Laplace transform, f1 of s plus c2 into L inverse of f2 of s. This is the linear property in the inverse Laplace transformation. Next, some problems. Evaluate inverse Laplace transform of the following. First one, L inverse of 1 by s to the power of 5. So which is equals to L inverse of 1 by s to the power of 5 can be written as s to the power of 4 plus 1. Just now we written n is positive integer. What you are going to write? It is 4 factorial divided by t to the power of 4 divided by 4 factorial. Is it clear? L inverse of 1 by s to the power of n plus 1 is equal to n is being positive integer. Here it is t to the power of n divided by n factorial. This is the answer. Next, L inverse of, evaluate L inverse of 1 by root s. So which is equals to L inverse of 1 by root s, 1 by s to the power of 1 by 2 we have. Here it is not a positive integer. Here can write it some constant plus 1. So how we can write it this, which is equals 1 by 2 can be written as L inverse of 1 divided by n plus 1. N plus 1 will get the minus 1 s to the power of minus 1 plus 1 by 2. Sorry, 1 minus 1 by 2. Better to write it 1 minus 1 by 2. Is it clear? It is n plus 1 or minus 1 by 2 plus 1. No problem. Better to write it minus 1 by 2 plus 1. Here n is equals to what? Minus 1 by 2 is there. So which is equals to, by using this, t to the power of n divided by gamma of n plus 1. So which is t to the power of n divided, t to the power of n is nothing but t to the power of minus 1 by 2 divided by gamma of n plus 1. N plus 1 is nothing but minus 1 by 2 plus 1, which is t to the power of minus 1 by 2 divided by, it is gamma of 1 by 2. Gamma of 1 by 2 is equals to root pi. Is t to the power of minus 1 by 2 divided by root pi, which is equal to 1 by root pi t. This is the evaluation process, right? Why? Here it is 1 by 2 is not a positive integer, it is a real number which is greater than minus 1, right? So in the, we can write it 1 by 2 can be written as minus 1 by 2 plus 1. So minus 1 by 2 plus 1 we can write about, we have the formula L inverse of 1 divided by s to the power of n plus 1, n being real number. So we can write t to the power of n divided by gamma of n plus 1. This is the problem. Next. Next, third one. Evaluate inverse Laplace transform of 1 divided by 2s minus 5. For finding the Laplace transform, function of t is given. For finding the inverse Laplace transform, function of s is given. So L inverse of 1 divided by 2s minus 5. So to find this one, I am going to write, this can be written as L inverse of 1 divided by 2 into s minus 5 by 2. So if this is, I am going to go for apply the linear property. 1 by 2 is a constant. L inverse of 1 divided by s minus 5 by 2. So it is in the form of 1 by 2 into inverse Laplace transform of s minus a, which is e to the power of at. So a is equals to what? 5 by 2. E to the power of 5t by 2. Next, like this we can evaluate it as L inverse of s divided by s square plus 16, direct principle. L inverse of s divided by s square plus 4 square. So L inverse of a Laplace transform of, just to apply the, to write the inverse Laplace transform of function of s, just you recall the Laplace transform of the function of t, then we get the clarity. Inverse Laplace transform of s divided by s square plus 4 square, you know that this is the Laplace transform of cos at. When it is a Laplace transform of cos at, yes, cos at is the inverse Laplace transform of this one. So which is equals to cos 4t. Yeah. If you have the problem like this, L inverse of some 1 divided by s square plus 16. What I am writing? L inverse of 1 divided by s square plus 16 is same as 1 divided by s square plus 4 square. But you know that if what you are going to expect, if 4 is there, you can write it sin 4t. Yes, 4 is not there, you can write it sin 4t divided by 4. Yes, that is considered to be formula. So multiplying with 4, dividing with 4, you can get direct principle you will get. If you are multiplying with 1 by 4 of L inverse of 4 divided by s square plus 4 square, so which is 1 by 4 into sin 4t, that is nothing but sin 4t divided by 4. Like this we can evaluate it. These are the simple problems. Next, the same way We are trying to evaluate, suppose if we take the fifth problem, Laplace transform of 2s minus 5 divided by s square minus 9. Right, this can be written as inverse Laplace transform of 2s by s square minus 9 plus minus 5 divided by s square minus 9. Yeah, which is 2 is a constant, L inverse of this can be written as s divided by s square minus 3 square. Okay, next minus 5 into L inverse of 1 divided by s square minus 3 square. Given the formula L inverse of s divided by s square minus a square is equals to cos hat. L inverse of 1 divided by s square minus a square is equals to 1 by a sin hat. So here it is 2 into a is equals to 3 is there. What cos h3t here? Minus 5 into sin h3t. Yeah, this is the inverse Laplace transform of the function. Next. Next, I am going to take it the same way. You are going to complete these problems. 3s minus 16 divided by s square minus 16. Seventh one, L inverse of 1 divided by s to the power of 7 by 2. So see this one. Here it is L inverse of 7 by 2 can be written as 1 s to the power of 5 by 2 plus 1, right? 5 by 2 plus 1. S1 by s to the power of n plus 1. As 5 by 2 is not an integer, so it is a real number or rational number, that belongs to the real number. So what we have, t to the power of n divided by gamma of n plus 1, which is t to the power of n, it is nothing but n is equals to 5 by 2 is there. T to the power of 5 by 2 divided by gamma of 5 by 2 plus 1, it is 7 by 2. T to the power of 5 by 2 divided by gamma of n is equals to n minus 1 gamma of n minus 1. So n minus 1, 7 by 2 minus 1, that is 5 by 2 into gamma 5 by 2, yes, which is t to the power of 5 by 2 divided by again 5 by 2. Yes, gamma of 5 by 2 is what? 5 by 2 minus 1, 3 by 2 into gamma of 3 by 2. Yes, gamma of 3 by 2 is what? 3 by 2 minus 1, that is 1 by 2 into gamma of 1 by 2. It is gamma of 1 by 2. How many 2's are there? 1, 2, 3. 3 2's. 2 to the power of 2 cube. That is 8 t to the power of 5 by 2 divided by 5 into 15. Gamma of 1 by 2 is equals to root pi. This is the inverse Laplace transform of 1 by s to the power of 7 by 2. Next. In the same way, we are trying to solve this, compute the inverse Laplace transformation. 3s minus 2 divided by s to the power of 3 by 2, separate the terms, plus root s minus 1 whole square divided by, root s minus 1 by s whole square plus 4s minus 18 divided by 9 minus s square. You take out the this is a common, minus is a common, right? Evaluate it. Next, ninth one, L inverse of this. These are the elementary function. By using the previous principles, you will get the s square minus whole square by 2s to the power of 5 plus 4s minus 18 divided by 9 minus s square plus s plus 1 into 2 minus root s divided by s to the power of 5 by 2. Next, solve these problems. Next one, show that 10th one, show that inverse Laplace transform of 1 by s cos 1 by s is equals to 1 minus t square divided by 2 factorial whole square plus t to the power of 4 divided by 4 factorial whole square minus t to the power of 6 divided by 6 factorial whole square plus so on. Right, here it is. First I am writing the cos x expansion. You know that cos x Maclaurin series expansion is cos x is equals to, just I am trying to recall the Maclaurin series expansion of cos x. Cos x is equals to 1 minus x square or x square by 2 factorial plus x to the power of 4 divided by 4 factorial minus x to the power of 6 divided by 6 factorial plus so on. But here it is cos 1 by s is there. Cos 1 by s is equal, so just you replace x with 1 by x. So 1 minus 1 by s whole square, that is 1 by s whole square by 2 factorial 1 by s whole to the power of 4 divided by 4 factorial 1 by s whole to the power of 6 divided by 6 factorial plus so on. Yeah, which is same as 1 minus 1 by 2 factorial into s square plus 1 by 4 factorial into s to the power of 4 minus 1 by 6 factorial into s to the power of 6 plus so on. So on. But this is about the cos of 1 by s. Next I am going to take 1 by s into cos 1 by s. So which is 1 by s minus 1 by 2 factorial into s square, it is s cube plus 1 by 4 factorial into s to the power of 5 minus 1 by 6 factorial into s to the power of 6 plus so on. Taking inverse Laplace transform on both sides, 1 by s cos of 1 by s is equals to, so applying the linear property here, L inverse of 1 by s, direct I am writing here 1 by 2 factorial of L inverse of 1 by s cube can be written as, direct I am writing it is 2 plus 1 here plus 1 by 4 factorial L inverse of 1 by s to the power of 5 is there, that is 4 plus 1 so minus so on. But you know that L inverse of 1 by s is equals to 1 minus 1 by 2 factorial 1 by s to the power of n plus 1, when n is positive integer it is n factorial, t to the power of n divided by n factorial, that is here n is equals to 2 is there, t square divided by 2 factorial, here it is 1 by 4 factorial into it is t to the power of 4 divided by 4 factorial, next 1 by 6 factorial we have, here it is s to the power of 6 can be written as s to the power of 5 plus 1. So in this case not s to the power of 5 is there, here we will get s to the power of 7 will get when we are multiplying with 1 by s. S to the power of 7 can be written x to the power of 6 plus 1. So it is t to the power of 6 divided by 6 factorial. If you are simplifying it, you will get this term, right? 1 by t 1 minus 1 by 2 factorial into 2 factorial whole square plus t to the power of 4 divided by 4 factorial into 4 factorial whole square minus t to the power of 6 divided by 6 factorial whole square. This is a problem. In the same way, you are going to complete these two problems. Eleventh one, show that L inverse of cos I taken, now I am going to take the sin 1 by s, which is equals to t minus t cube divided by 3 factorial whole square plus t to the power of 4 divided by 5 will get odd powers, 5 divided by 5 factorial whole square minus t to the power of 7 divided by 7 factorial whole square plus so on. Next, that is 12th one, show that L inverse of 1 by s e to the power of minus 1 by s here it is, which is the same as we'll get the answer 1 minus t square by 2 factorial, t cube divided by 3 factorial whole square, 1 minus t plus t square divided by 2 factorial whole square minus t cube divided by 3 factorial whole cube plus so on. But you are going to write the Maclaurin's expansion for e to the power of x. You know that here it is in case of sin 1 by s, what I am writing? Sin 1 by s, sin x Maclaurin's expansion is, or Taylor's expansion about x is equals to 0 is x minus x cube divided by 3 factorial plus x to the power of 5 divided by 5 factorial minus x to the power of 7 divided by 7 factorial, so on. In the same way, e to the power of x expansion, you know that e to the power of minus x expansion for the this problem. Here it is, here all positive terms are there, e to the power of x. Here it is alternatively positive and negative. 1 minus x plus x square by 2 factorial minus x cube by 3 factorial plus so on, right? These are the problems. Next. Next problem. Next, show that integral 0 to infinity cos of tx square dx is equals to 1 by 2 into pi divided by 2t whole to the power of 1 by 2, and also find integral 0 to infinity cos x square dx. Right. Listen. Now using the inverse Laplace transformation and transformation concept, Laplace transformation concept, now I am going to evaluate. Coming to the solution. Let f of t is equals to, I am taking, it is a function of t, no? Here it is clearly it is a function of t I am taking. Here tx square is there, no? So f of t is equals to integral 0 to infinity cos x square t or tx square dx. Now I am going to find the Laplace transform of this one. Now Laplace transform of f of t is equal to, from the definition, Laplace transform of f of t is equals to, from the definition of the Laplace transform, integral 0 to t e to the power of minus st f of t dt. Here f of t is what? This one is there, no? So that implies Laplace transform of integral 0 to infinity cos tx square or x square into t, whatever it may be, x square into t dx is equals to integral 0 to infinity e to the power of minus st. F of t is replaced by what? Integral 0 to infinity cos x square t dx of, sorry, it is dx of dt. Yeah. Now I am going to change the order of integration, right? First integrating, changing the order of integration here. Integral 0 to infinity, why? The limits are same. E to the power of minus st, here it is cos x square t dt changing the order of integration to integral 0 to infinity of dx. Is it clear? Now I am going here, this is the integration with respect to x, this is the integration with respect to t, by changing the order of integration. Here it is clearly, what do you write? Here it is e to the power of minus st cos x square t dt. Here it is cos at. This is nothing but Laplace transform of, this is same as cos at, cos in place of a, this is a, when we are integrating with respect to t, keeping x square as constant here. So this can be written as integral 0 to infinity. This is the Laplace transform of cos x square into t dx. So this is same as integral 0 to infinity. This is same as, here it is, cos at, Laplace transform of cos at is equal to s divided by s square plus a square. Here s is nothing but here s divided by s square plus a square. A is equal to x square is there. Here it is x square whole square. Here it is dx. Clear? This is same as this is integral 0 to infinity s divided by s square plus x to the power of 4 dx. Now to evaluate this, I am going to take one substitution here. X is equals to s tan theta. Put x is equals to s tan theta, or x square is equals to s tan theta. That implies x is equals to root s tan theta. Right, the dx by d theta is equals to what? Dx by d theta is equals to, differentiating with respect to theta, 2x dx by d theta is equals to s into tan theta derivative is secant square theta here. That implies dx is equals to s secant square theta divided by 2x d theta, which is same as s into secant square theta is nothing but secant square theta divided by 2 into what we have, x is equals to root s tan theta d theta. This is nothing but dx. Now the limits are x is equals to 0, that implies root s tan theta is equals to 0, that implies theta is equals to 0. X is equals to infinity, that implies root tan theta is equals to s tan theta is equals to infinity. As here it is, s is a constant, it cannot be infinity, it is tan theta is equals to infinity, theta is equals to pi by 2 here. Now the integration becomes, if we use the substitution, the integration becomes integral theta is equals to 0 to pi by 2 as s into x square plus x square, that is s square, or s into s square plus x square is equal to what? S square tan square theta. X square is equal to s tan theta, but dx is equals to s secant square theta divided by 2 root s tan theta d theta. So integral theta is equals to 0 to pi by 2 s into s square secant square theta divided by, if we common s square, 1 plus tan square theta into, here it is 2 root s into root tan theta d theta. S square get cancelled, secant square theta, 1 plus tan square theta, the secant square theta get cancelled. We have integral or 1 by 2 root s root tan theta, it is nothing but g theta is equal to 0 to pi by 2 root tan theta, it is root cot theta, 1 by root tan theta, it is root cot theta, is d theta, which is same as 1 by 2 root s integral theta is equal to 0 to pi by 2 root cot theta, it is same as sine to the power of minus 1 by 2 theta cos to the power of 1 by 2 theta. If you go for the beta gamma functions, you know that beta gamma functions integral theta is equals to 0 to pi by 2 sine to the power of mx or sine to the power of m theta cos to the power of n theta is equal to 1 by 2 into beta of m plus 1 by 2 comma n plus 1 by 2. Right, converting into beta functions, it is 1 by 2 root s into 1 by 2 into beta of, here m is equal to minus 1 by 2 is there, minus 1 by 2 plus 1, it is 1 by 2, 1 by 2 by 2, that is 1 by 4. Directly I am writing here by using that. Next 1 by 2 plus 1, that is 1 by 2 plus 1, it is 3 by 2, 3 by 2 divided by 2, that is 3 by 4. Is it clear? Which is 1 by 4 root s beta of m comma n is equals to gamma n divided by gamma n plus 1, gamma 1 by 4, gamma 3 by 4 divided by gamma of 1 plus m plus n, 1 by 4 plus 3 by 4, that is 4 by 4, it is nothing but gamma of 1. Now continuation, which is 1 by 4 root s. Here gamma of 1 by 4 can be, it is gamma of 1 by 4 into gamma of 3 by 4, 1 minus 1 by 4 divided by gamma of 1 is 1, which is 1 by 4 root s into gamma of 1 by 4, gamma of p, we have one property here, gamma of p into gamma of 1 minus p is equals to pi divided by sin p pi. Pi divided by sin p pi we have. So pi is equals to pi divided by sin p pi. P is equals to 1 by 2 is there, 1 by 4 is there, 1 by 4 into that is sin pi by 4. So which is pi divided by 4 root s into sin pi by 4 is equals to 1 by root 2. So which is root 2 pi divided by 4 root s. Again this can be written as, yes, root 2 get cancelled, 1 pi divided by 2 root 2s, root s. This is the value of Laplace transform of f of t is equals to pi divided by 2 root 2s. But actually we have, I'm going to replace f of t integral 0 to infinity cos x square t dx is equals to pi divided by 2 root 2s. Yeah, now you take out this term, we need to evaluate this one, right? Integral 0 to infinity cos x square t dx is equals to L inverse of pi divided by 2 root 2s. So pi divided by, here what we have, it is 2 root 2 is a constant here, L inverse of 1 divided by s to the power of 1 by 2, which is pi divided by 2 root 2. S to the power of 1 by 2 can be written as 1 minus 1 by 2, yes, m minus 1. So 1 by 2 minus 1 by 2 plus 1, minus 1 by 2 plus 1. So here it is L inverse of 1 divided by s to the power of n plus 1, we need to write it, minus 1 by 2 plus 1. Here n is equals to minus 1 by 2 is there. Yes, n not integer, so it is t to the power of n. So which is pi divided by 2 root 2 t to the power of n. T to the power of n is nothing but 2 root 2 t to the power of minus 1 by 2 into gamma of n plus 1, minus 1 by 2 plus 1. It is 1 by 2 here. Continuation, which is equals to pi t to the power of minus 1 by 2 divided by 2 root 2, root 2 into gamma of minus 1 by 2 plus 1 is what? Gamma of 1 by 2. Gamma of 1 by 2 is equals to, gamma of 1 by 2 is root pi. root pi, which is equals to, we'll get the answer here, which is 1 by 2 into, yeah, you take out this one to the denominator and root pi get cancelled. It is 1 by 1 divided by pi divided by, we'll get the pi in the numerator, right? Pi divided by root 2t whole to the power of 1 by 2. This is the value of integral 0 to infinity cos x square t dx. If you take t is equals to 1 here, integral 0 to infinity cos x square dx is equals to 1 by 2 into integral pi divided by root t whole to the power of 1 by 2. Pi by 2. In the same way, you are trying to solve this one. Show that integral 0 to infinity sin t into x square dx is equals to 1 by 2 into same answer, pi divided by 2t whole to the power of 1 by 2. From this, evaluate sin x square dx 1 by 2 into pi by 2 whole to the power of 1 by 2. Next, third one. Show that integral 0 to infinity e to the power of minus tx square dx is equals to 1 by root pi by t, or by using this integral 0 to infinity e to the power of minus x square dx is equals to root pi divided by 2. These are the problems we are going to solve. Next class we go for the evaluation of the inverse Laplace transform by using the method of partial fractions.